Hi everyone, I'm Anna Liu. What a great honor and privilege to be given this award. We are so excited to be here at ICPE with you. Many thanks to the awards committee for your recognition, and huge thanks to the ICPE research community of colleagues and friends right across the world. For many years now, ICPE has been one of my favorite and most productive conferences. On behalf of our team, I'd like to thank you for your inspiration, collaboration, and support. Together with Professor Alan Fekete, 12 years ago, when cloud computing was in its early days of development and adoption, with the funding support from the Australian government, we established a cloud computing research group. We brought together PhD students, postdocs, researchers from various Australian universities, drawing upon expertise in distributed computing, software engineering, databases, networking, and of course, performance engineering. This paper being recognized today, I am very proud to say, was the core work carried out by Dr. Sadiqa Islam, who not only successfully completed her PhD requirements in 2016, Sadiqa also received the Best PhD Thesis of the Year award from University of New South Wales. Now I'd like to introduce you to my esteemed colleagues, Kevin, Alan, and Sadiqa, who will share the context that led us to the research focus, the key ideas and contributions in the paper, and some of our reflections since then.
Hi, my name is Kevin Lee. Let me provide a bit of context to our research work. If we go back in time, about 10 years ago, you would find most of the major cloud providers you see today were already there. AWS, Azure, or Google Cloud. They were already key players in the cloud space and providing quite a wide range of service offerings. At the time, companies, especially enterprise, were trying to evaluate the use of cloud. They wanted to understand if there's any cost benefit in using the cloud, and at the same time, meet their functional and non-functional requirements. For things like performance or availability, these are well understood, and they know how to measure them quite well, whether it's cloud or non-cloud. However, the concept of elasticity was relatively new at the time. It's often highlighted as a key benefit of using the cloud, but it was not clear what that really means in practice. In particular, how could one measure elasticity in a quantitative manner? How elasticity impacts the cost of running a system? What characteristics of a platform influences elasticity? Our research was an attempt to answer these questions from the viewpoint of a cloud consumer. I'll hand it over to Professor Alan Fekete to talk more about our research. Thank you.
Hi, I'm Alan Fekete, and I'm going to talk about the biggest ideas that were in our paper 10 years ago. We took the view that measuring the elasticity of a platform should focus on what matters to the consumer who is paying for services on that platform. So the consumer, the value that they get from elasticity is only pay for what you need. So our attempt to measure elasticity started around that. We take a workload, submit it to a platform, and then measure two sorts of penalties that the consumer faces. One is just the money they have to pay for the platform, and specifically what we measure is the difference between what they pay and the resources they actually need to deal with the workload that is being supplied. So that includes situations where, for example, they've asked to give up a resource, but the system delays spinning it down. Or in those days, there were cases where the platform would keep charging for a resource, say to the end of an hour, even after it was no longer being used. The other side of the penalty that a consumer faces is if they don't have sufficient resources. And we measured that in terms of client-specific figures for how much disadvantage they suffer from each service level agreement that gets violated from not having enough resources. We do this for a number of different workloads in our benchmark. So a sinusoidal workload, an exponentially bursty workload, a steadily linearly growing workload, and so on, and then combine all of these with a geometric mean. So where has this work led? Since we did the work, there really has been a broad agreement that elasticity is one of the central aspects that a benchmark for a cloud platform should include, and also that the elasticity measure should reflect those issues of what matters to the consumer, especially the costs that are incurred from having resources unnecessarily, paying for them, and having insufficient resources. So this has really been established into the field, and there have been quite a lot of papers that have dealt with this.
Hi everyone, my name is Sadika Islam. Now I'm going to talk about the reflections part. In the reflections part, we address the criticisms provided by the Elasticity community. Special gratitude to those who provided constructive criticisms to our work. The first criticism we received is the lack of workload customization from traces. We provided a workload modeling approach that can reproduce the prototypes of fine-scale bursty workloads to address such criticism. This workload model can preserve statistical regularity behavior at a small time scale. This work got published in the paper evaluating the impact of fine-scale burstiness on cloud elasticity at SOCC 2015. Below is the Wikipedia workload snippet and the corresponding fine-scale bursty prototype. In the Wikipedia workload snippet, noises are more at the peak and less at the trough. This amplitude-noise correlation is strictly maintained in our created fine-scale bursty prototype. The next risk factor is the influence of performance variability in the cloud on the elasticity metric. This can cause inconsistent elasticity benchmarking results for the same workload across various runs. We provided a solution to this problem by listing a set of strictures based on statistically rigorous experiment design and analysis. For example, workload suite diversification, setup randomization, blocking, and specifying the confidence interval for the elasticity metric in the data analysis part. Let's take the setup randomization. In the setup randomization technique, benchmarking is replicated in different randomized setup. For example, if there are 3 availability zones and 7 days of the week, there will be a total of 3 multiplied by 7, 21 randomized setup. Setup randomization suggests taking benchmarking reading in a subset of these randomized setups. This work got published in the PhD thesis Elastic Mark and Elasticity Benchmarking Framework for Cloud Platforms from UNSW in 2016. An additional benefit of our work is that it provides a heuristic for the cloud providers too, to perform head-to-head comparison of multiple elasticity products in the market and identify their own flaws or shortcomings. It is positive to see that our work got approved by the cloud providers too. For example, Microsoft Azure charging quanta got reduced from clock hour to a minute only. AWS Lambda now charges based on the number of requests and duration of execution only. Therefore, our work has a positive impact on the elasticity of the cloud offerings in the market. Thank you, everyone.